Good morning, one and all present here. We are starting for the day 4 technical sessions. In this 1 week AICT RGPV joint 1 week online teachers training program on applied natural language processing. I heartily welcome our today's resource person for the forenoon sessions, Dr. Chandresh Maurya from IIT Indore. I am very much thankful to Chandresh sir for sparing his time with us in this online TTP. I also welcome all the faculty participants for this session. Chandresh Kumar Maurya has been working as an assistant professor in the CSE department of IIT Indore since July 2020. Before that, he worked as an assistant professor at NIT Delhi and ELTE University, Budapest, Hungary. He also worked as a research scientist at IBM Research Bangalore from 2017 to 2019. He did his PhD at Indian Institute of Technology, Roorkee in 2016. He completed his master's degree from JNU New Delhi in 2012 and BE from BIET Jhansi in 2010. He is the proud recipient of Prime Minister's Fellowship for the doctoral research awarded by the Confederation of Indian Industries and Robert Bosch, Bangalore. He won the Best Poster Paper Award at Xerox Research Center, India in XRCI Open 2016 and interned at Microsoft India R&D department at Bangalore and Research and Technology Center at Robert Bosch, Bangalore, India in 2014. It's our great pleasure to have such an eminent researcher with us to share the knowledge for the broad domain of natural language processing. I once again thankful to Chandresh sir. Sir, let me just brief you what we have covered till now and what is the background of faculty participants. We are having the faculties for Madhya Pradesh State Technical University affiliated institutions from Madhya Pradesh and AICT affiliated institutions in India. We are having majority from computer science and information technology and relevant disciplines, and we are also allowed some interdisciplinary faculty participants who want to upgrade themselves in the broad domain of AI, that is NLP. And I'm once again very much thankful, and we are eager to hear you, sir. With such a great background of variety of domains and the really prestigious workplaces, it's our pleasure to welcome you. I now request Dr. Chandresh to take over the mic and start the session.
Thank you, Dr. Meg, for the wonderful introduction, and I welcome everyone to in this session. And I hope you had a good 3-day session in the past, and this is the 4th day, I guess.
Yes,
okay,
sir.
So
today and certain NLP basics, some ML models, then BERT Google model, and some Anaconda-based certain case studies like taking out the trending topics from Twitter are the salient things which we have covered.
Okay. Just a second, give me 10 seconds.
Yeah, I think you are getting the rights to share your screen.
Yeah, okay. So that means I hope people are comfortable with basics of NLP, because what I'm going to cover, the topic is relation extraction. I think sequence tagging has already been covered by some professor. So I'm going to talk relation extraction in particular. Okay.
Right, sir.
So that's
sir,
the agenda. Let me share my screen.
Just a minute, sir. We will be sharing your PPT afterwards. to the participants. We are recording the session. So is it possible for us to share your recording on YouTube?
Okay, no problem.
Right, right. Okay,
No
sir.
issue.
Please
Okay,
proceed.
okay, okay. I see. My screen should be visible now.
Right, right, sir. Perfect.
Okay. Yeah, so the topic is relation extraction. The slides are adapted from the lectures of Bill McCartney from Stanford. Okay, so yeah, so this is the overview of the talk. First, I'm going to talk about what is a relation extraction, why this is one of the very hot topic nowadays in NLP domain. Okay, and why it is important. Then we'll talk about what are the data resources. Let's say if you are looking at solving, or if your application wants to use this relation extraction, what are the data resources that you can use, followed by the problem formulation, how to formulate. Let's say you want to do relation extraction, then what kind of problem it eventually boils down to, whether can we use multitask learning, or let's say supervised learning, or any other clustering technique, for example. What kind of technique can be used to solve relation extraction? Then we'll go to the evaluations of those solutions, and followed by some baselines, and what are the future directions to explore after this talk. Okay, and I suggest and encourage everyone to ask questions in case you have any doubt, so that we can make it more interactive and beneficial to you. Okay, all right, so let's understand what is a relation extraction and why this is important. So the task of relation extraction, first I'll talk about the task definition, what is a relation extraction, then what is the goal behind doing this task, why we are interested in relation extraction after all, right? Then we'll look at some practical applications, and then we'll see how this problem is solved, okay, using, let's say, supervised learning and then distance supervision. Okay, so the task definition. The task of relation extraction is one of the core problems in NLP. The idea is that, let's say you have been given some corpus, and corpus in NLP is kind of bunch of data, the text data in particular. The data could be, let's say you have collected news corpus, you have collected the Wikipedia pages, that is your corpus, right? So from this corpus, from this data, the idea is to extract triples. Triples are basically the kind of here that you are seeing on the right side. So from this corpus, what you are gathering is these relations where there is a subject, there is an object, and what kind of relation exists between these two subject and objects, right? Sometimes we call these subjects as entities. So the idea is that given two entities, what kind of relation exists between them. So that's the problem of relation extraction. So here in this case, you can see that Elon Musk, the PayPal are related with this relation, the founder. Okay. Similarly, Elon Musk and SpaceX is again, they are connected. The two entities are connected using a founder relation. And there are, now you can see that between the two entities, or the same relation can hold between different pairs of entities, or same pair of entity can have multiple relations as well. Okay, so that's the idea, and this is the task. Okay, whenever I'm saying the task is to extract such triples, okay, where you are finding the relation as well as the two entities. Okay. So there was a famous quote by one of the renowned professors of AI, Tom Mitchell, in 2005, and he predicted that if you read this red text, it is saying that by 2015 we will have a computer. So this statement was made in 2005. So at that time, like 15 years ago, he said that in 2015 we will have a computer program capable of automatically reading at least 80% of the factual content on the web, placing those facts in a structured knowledge base. Okay, so nowadays we can see for example, Google, when you search something, let's say you search Prime Minister Modi or something else, then you see something coming up on the right side, the search result, okay, where the information about, let's say, Prime Minister Modi is put in a more structured format, right? It tells, okay, what is the date of birth, what is the, place of birth, and so on, okay? So these things are actually coming from a knowledge base that we also call sometimes such a knowledge graph, okay, where the nodes in that graph are the entities and the edges denote the relation between those entities, okay. So now you can see that to represent unstructured data to a structured format, we need a knowledge base, and the knowledge base actually is populated by using these triples, and to extract this triple is the task of relation extraction, okay. So that's the whole idea of doing relation extraction, and it has lots of applications which are we are going to see next. Yeah. Okay, so the task of relation extraction, it finds applications in, for example, the intelligent assistants. Nowadays, all of us have these smartphones, right? And we play music and so on. So the way these musics are stored by, let's say, categories, depending on who is the, uh, creator of that particular track, right? So you can see that here, the OJ's love train. So OJ's is, I guess, the artist, and this artist, created this track, the love train. Okay. So here on the right side, what you see is the corpus of the data. From that corpus, when you extract the relations, then you put them in this format, and this format can be used to play music based on, let's say, artist, or based on the track, and so on. And yeah, these intelligent assistant systems, they use such things, the relation extraction, right? Similarly, you can use relation extraction to build ontologies, right? Here, I guess it's more of in a video game. Another domain would be when I was working in IBM. So we were talking about building ontology for a product domain, right? For example, when you search Amazon website for a particular product, it lands up with a page where you see there is a product, there is a seller, okay, and many other details about that product are there. And on the top, you'll see that there is a product hierarchy, the way this product is categorized. Like you first go to, let's say, electronics. Within the electronics section, you go to the, let's say, music section, and in the music section, you are searching, let's say, iPod or some other stuff, right? So the way these items are categorized, they again, that's actually your ontology, right? And in order to store these items of interest in a particular structured format, we need these relations, right? So that we can categorize in a proper way, okay? Similarly, the task of relation extraction finds application in gene regulation, those who work in the biology domain, right? So nowadays there are lots of articles from coming from, let's say, this bioscience and biotechnology people, right? So lots of articles are there. So you can actually consume this corpus, let's say, research papers, and based on this research paper, if you run, let's say, relation extraction, what you can do, for example, in this case, you can extract the genes, let's say a pair of genes which are interacting, and in the way particular way they are interacting. So interaction pattern would be the relation, and the two genes would be the two entities you can think of, right? So here in this knowledge base, you are seeing that there are subject and object. So you can see this gene has this interaction with this protein using this relation. So P53 is a protein, okay? So if you run the relation extraction on such corpus, you will get such relations. So these things can help you identify, the relation extraction task can help you identify whether P53 is a protein, or if two, what is the interaction pattern of two genes, okay? If let's say, what is the effect of certain medicine on certain disease, and so on, you can extract all kind of things from this corpus, right? using relation extraction. So that's why this is like, it has enormous application in various domains. Okay. Oh, yeah. So, I mean, this is the one of the subset of the relation extraction applications. Now you can ask, if you want to solve this relation extraction problem, what are the different ways to solve this issue? Okay. So I hope everybody till now is clear what is a relation extraction. If in case it is not clear, then let me know. Okay. So that I'll try my best to answer this. Does anyone has any?
Chat box, there is one question.
Okay, let me open that. Yeah, so you can also type your questions there. Okay, just a second. Yeah. What is a triple? I'm not able to understand. Good. Yeah, I encourage you to ask simple question. Even the simple question, maybe you might feel this is a dumb question that you're asking, but actually even dumb question are sometimes they make sense, right? So if you don't understand, then I encourage you to ask. Okay, don't think that okay, this is very trivial question, I should not ask and so on. So don't think like that, ask. Okay, so triple, when I'm saying triple means three things should be there. Okay, so in relation extraction, what is a triple? The two entities. Okay, and the third thing is the relation between those two entities. For example, if I give you an example, if I give you two entities, so I don't know if you are familiar with the entity term. What this covered entity thing in the previous NLP lectures? Anyone familiar with what is an entity? So I was assuming people know what is an entity.
Sir,
Yeah.
am I audible?
Yes, yes.
Anything with which you can associate some properties, attributes that can be treated
Yes.
as an entity. It may be physical or it may be logical.
That's correct. So entity, when I'm saying entity, is something which has certain properties. Okay, certain attribute can be associated. So that's an entity, and usually an entity is a noun phrase. Okay, so, and for example, if I say Narendra Modi or the Prime Minister, okay, so India. So country names are entities, people names are entities. Okay, objects names are entities, protein name is an entity, and so on. Okay, so if I say Narendra Modi and India, these are the two entities. And if I ask you what is the relation, between these two entities, then you can identify. Okay, Narendra Modi, India, and the relation between them is a prime minister of. Okay, so Narendra Modi is the prime minister of India. So now we have three things: two entities, Narendra Modi and India, right? These are the two entities, and the relation is prime minister of. So that's why we call it as a triple. Okay. Any other question? So our goal is to identify such triples from the corpus, and corpus is, for example, news corpus, news data. Let's say you crawled some news websites or you crawled Wikipedia pages and so on. So given this unstructured data, you want to build a knowledge base of triples. Okay, and why we are doing that? Because it finds applications in various domains to help categorize the product over, let's say, Amazon site, or it helps you identify what is the effect of a particular medicine on a particular disease and so on, right? So that's why we want to extract these triples. Okay. All right, so let's move on. So that's the problem we want to solve. The question is how to do it. Anyone has any ideas what should be the starting point? Let's say if somebody asks you, okay, here is the corpus, maybe you have access to all the Wikipedia pages, and from the Wikipedia pages you want to extract all the triples which are there. Okay, what would be your starting point? How would you solve this problem? People, you can throw your idea, thoughts, so that it's more interactive. You should be emotionally attached to the lecture. if you are thinking and trying to come up with a solution, it will help you understand the concept more.
I think, sir,
Not audible.
we are having, if we are having text data, then first of all, we have to tokenize it so as to find out the entities.
Yeah.
Sir, we have to first clean the data,
Okay.
because pre-processing of data is much required.
Yes. Okay.
So this will be the first
Fine.
step, I suppose.
Okay. After that, yeah, pre-processing is like kind of one of the first steps. Let's say you tokenize the data. Yeah.
Remove the unwanted things from the data, like extra tags or
Okay.
characters which are or emoji, like unwanted things which are there in the data. We can remove that after processing.
Okay, let's say I have done that. I have given you the clean data. I removed all the, punctuations and stop words. I removed double quotes and so on. Okay, I tokenized and segmented the sentences also. Okay. After that, what would be the approach to extract these triples? How do you go about solving this one?
So
Like naive approach,
sir, I
simplest
guess
approach you
according to
can
the
think of. Yeah.
according to the requirement, what is our requirement? Like if we want to process the speech data, then uh, first we remove the unwanted things. After that, the sentence can be tokenized into single words, like and we have different steps for that, like syntactic analysis, semantic analysis, that type of things can be done.
Mm-hmm. Yeah, so this is what I'm already giving you. You have pre-processed data, okay? I have already given to you. So from that, you need to extract these triples. For example, let's say some sentence has this reads like, okay, Narendra Modi is Prime Minister of India, which is, and who resides in New Delhi and so on. So this kind of sentence is there. Now you will need to extract these things, Narendra Modi, India, and that relation between that. Okay. So people are saying
Like
parsing is needed. Okay.
sir,
Word
like
embedding.
generally in a sentence, triples, like if in a mathematical way, if I can explain, then different arguments are there, different operands are there, then we distinguish that in different fields.
Yeah, quite close. You're very close to that one. So what you are suggesting is to write a mathematical pattern for that, right? So
Yes, sir.
yes, quite a good answer. I like that. So the first step would be to design. See, in any machine learning or NLP techniques, if you want to solve some problem, you need some features, some ways to extract the data from that unstructured data, right? So the naive approach or the simple approach would be to write rules, handwritten rules, right? So I can write, let's say I want to extract all the relations, all the triples which where the relation is prime minister of. Okay. So if I search for all the patterns by handwriting these patterns, okay, and also mention, okay, um, or if I'm just searching is prime minister of, and this pattern is searched over all the Wikipedia pages, then I will find many triples, right? Because in one Wikipedia page about India, so there would be a triple, okay, Narendra Modi is prime minister of India. And if you are crawling the, let's say, UK website, then each prime minister of relation also holds there, and the wiki page will say, okay, Boris Johnson is prime minister of UK, right? So if you have written a pattern, okay, regular expression, then you can easily extract such relations, right? So that's the like naive or simplest approach you can think of to solve this problem. So that's the next topic coming up in the slide. Okay, so let's see. Okay, so let me zoom it. Okay, so this is the, if you want to solve the relation extraction problem, the first approach would be hand build pattern. So this was the approach used in the late 1960s and 70s. Okay, and people used to write rules to extract patterns. So let's say you have written this rule. So you have three rules. X is the founder of X, who founded Y, or Y was founded by X. Okay. So if you search these patterns in your corpus, you will encounter sentences, okay, where this pattern is matching, you will extract those sentences, right? And you can see, okay, X can be replaced by Elon Musk. This Y can be replaced by SpaceX, and is the founder is the relation between them. So you have found this triple. Similarly, you have found a triple and so on, right? So you can proceed in this fashion, but there is a catch here, right? The catch is that if you are writing hard coded rules, then there would be sentences where these patterns don't fit. Okay, the same relation is there. For example, if you look at these sentences, so entity is the same. Elon Musk and SpaceX, the same entity, and the founder of his relation is there. But none of these pattern, handwritten pattern is matching. Okay, these regular expressions, you can think of these are regular expressions. So none of these regular expression is matching this pattern here. Okay, so this sentence will not be extracted using this technique, right? That means handwritten pattern is not scalable. Can you see what is the issue? If you are writing regular expressions, you have to either you have to write many rules to capture all of these different patterns, right? Which is not scalable. Okay, so that's the problem. Okay, so what to do, right? There's some issues. Somebody thought, okay, I'm gonna write some mathematical, rules or regular expression, and I'm trying to extract. That's fine, but it's not going to generalize to big data. Nowadays we are talking about big data stuff, right, where there are millions of relations and so on. So writing rules for all possible cases is not going to help you, right? Now you need to come up with another scalable solution. So can anybody throw some other ideas? How can we make the solution more scalable? Just think about it. If you, maybe to give you some hint, I suggest you can think of using supervised learning techniques. And I hope you are aware of what is a supervised learning technique. Can we use supervised learning technique to solve this problem?
Pardon, sir? Supervised or unsupervised?
Yeah, I believe that you are now convinced that regular expression based solution is not helping. The reason is that you cannot write all possible rules. Yes?
Yes.
Everyone agrees?
Yes.
Right? We cannot write all possible rules, as you saw in the previous slide, right? If you see this slide here, let's say you have written three rules, and these rules are not matching these lines, right? They are not fitting. So these lines will not be extracted. Now
Yes.
you're stuck. Then, okay, you can go and write another rule. X in bracket, founder of Y in a bracket close, right? Then you write another rule on top of that. Then it's not going to help at the end, right?
Yes.
So we need another scalable solution, right? Scalable means it can, extract different kinds of pattern and so on without manual work. That's why we want to do machine learning, right? Machine learning can help avoid, writing rules. So that was the feature engineering approach on old school ways. right, to solve this problem. Now we have this machine learning everywhere, deep learning maybe, right? So if I ask you, can we use machine learning to solve this problem? How would you do that?
There may be some there may be some kind of ambiguity, because it can be uh, all possibilities.
Mm-hmm. Yeah. Okay.
So it can be like a tree representation,
Mm-hmm.
a kind of like parsing tree representation, where it can be by left recursion or right recursion, something like that.
Mm-hmm. Okay, kind of. Yeah, so we are going to use supervised learning, or maybe using let's say building some classifier and so on, right? So this is what we are going to do. Okay, so let's see. Okay, so supervised learning. So the idea is that we are going to train a classifier, and if you want to train a classifier, you need labeled data, right? So let's say you are given these sentences coming from your corpus, and what you are going to do is whenever the two entities are related using a relation, for example, in this case, Elon Musk and SpaceX are related using this founder of relation, then you make it a label 1, okay? And whenever the relation doesn't hold between the two entities, you make it as no relation, or make it a 0. So you are basically building a binary label data, right? So tick mark is a 1 and cross is 0. You can assign classes, class 1 and class 0. So for example, in this case, entrepreneur Elon Musk announced the latest addition to the SpaceX, right? So this sentence is clearly indicating that Elon Musk and SpaceX are, it's not a relation basically. It is because Elon Musk is announcing the latest addition to the SpaceX, right? So there is no relation in this one. So you are marking cross checking, marking it cross, right? So that's how, if you want to train a classifier, you need to label your data in this fashion. Okay. Once you have this kind of binary labeled data, you can go ahead and train your favorite classifier. Maybe you can train a decision tree or SVM, right?
So, sir,
So good thing is
yes,
that,
excuse
yeah.
me, sir. So, like,
Mm-hmm.
is it something like that we can take it if we are having certain verbs? So, how those verbs
Okay.
are leading to its semantics? So,
Mm-hmm.
how to the one question is coming to my mind.
Mm-hmm.
Establishment, like establishing or founding and announcing, how to
Mm-hmm.
distinguish between these two actions?
Yeah. So the thing is that there are people, annotator, who read these sentences and then they will label the sentence whether there is a relation or not. Okay. So that's the problem. If you read this last line in the slide, it says that you need to label your data. Okay. So for example, if I ask you read this sentence and tell me whether there is a founder of relation between these two entities, what would you say? Whether there is a relation or not in this one?
Okay,
The
but
first one, right?
yes, there
There
is a
is, right?
relationship. Yeah.
There is a relation. So you'll make it as a 1 or tick mark, right? There is
Okay.
a. But when the annotator goes and read this sentence, and then the person finds, okay, this sentence is saying entrepreneur Elon Musk announced the latest addition to this SpaceX arsenal, right? So it's saying that, okay, Elon Musk is announcing something to add to the SpaceX company, right? So
Okay.
basically, intuitively, it is not saying that, okay, Elon Musk and SpaceX and Elon Musk are actually, connected using this relation. Okay. Similarly, Elon Musk tweeted Friday. So here, if you read this sentence also, right, here it's not a relation basically between the Elon Musk and SpaceX, right? Because Elon Musk is tweeting on Friday about something about SpaceX, right? So reading this sentence, I won't mark it as tweeted Friday relation holding between these two entities, right? So the annotator will do this after reading the text.
Okay.
All right. Yeah. Now, the good thing of this approach is that once you have got your sentences labeled by the annotator, you can train any classifier, SVM, neural network, or decision tree, anything, and it works. It can generalize well. Okay. The problem here is that you need to hire an annotator to, assign labels to these sentences. Okay. And if you have lots of sentences, you will spend good amount of money to get that data annotated. Yes. Now that's a big problem, right? Using supervised learning, that you need to have lots of labeled data. Now we are not in a good position to use supervised learning. Let's say you are running out of money, so you cannot spend money to get the data annotated. So what would be the solution? Can you think of another approach where we can solve this problem with less data and solve the same problem? What are the machine learning techniques when the data is less? What do you do?
Excuse me, sir. There is
Yeah.
one question in the chat box.
Okay.
What?
Yeah, I see.
Plus and minus the numerical quantity you have mentioned.
Yeah.
On the
Okay.
previous.
Yeah. Okay. Let me come to that one. Okay, where is my slide? Yeah. So these are basically the prediction scores. Remember when you predict using, let's say, logistic regression, right? Then you get some positive score, some negative score, right? If you have seen those who have done logistic regression, in logistic regression, for example, you get something between 0 and 1, some 0.5, 0.6. So it basically says the degree of this founder relation. The plus is basically how strongly the founder relation is between these two entities, Elon Musk and SpaceX. So this is the prediction made by the classifier. Okay. So this is that thing. Positive means there is the positive relation between these two entities, and negative score is basically saying that there is no such relation. Okay, announced is not a relation because it's negative 0.23. Okay, and so on. So that's the thing. All right. Yeah. So I was saying. Okay, so Mamta is asking graph representation of the text. Which graph representation? I don't know. Are you talking about this one, or I don't know which figure you're talking about? Okay. Okay. To answer, okay. She's answering the question. If you want to avoid the annotation, what to do? So your suggestion is to use graph representation of the text. Okay, fine. So how do you represent the text in the form of a graph? Because in order to build the nodes of a graph, you need to find the entities first. Yes. Then how do you find the entities? Or maybe you can talk about what would be the nodes in the graph. Okay. Anyone else wants to try? Okay, no problem. Let's see some other approaches. All right. So this supervised learning is not helping. So another technique that you can go and choose in machine learning, you might have heard of semi-supervised learning and unsupervised learning techniques, right? So you can go ahead and use supervised learning, and we use semi-supervised learning when we have, you know, less amount of labeled data and vast amount of unlabeled data, right? Those who are familiar with semi-supervised learning, we can certainly use that. Okay, but here in today's talk we are going to see some new thing. You might be aware of supervised, unsupervised, semi-supervised, right? But I don't know how many of you are familiar with distance supervision. Has anyone heard of distance supervision before? Transfer learning, distance supervision.
Yes, transfer
Yes,
learning.
sir. Yeah, transfer learning I have also heard, sir. That is being used now in this summarization of paragraphs. Now they are using that. I think Google
Yeah,
has
okay.
Google developers has come with this transfer learning models.
Yeah. Yeah, so distance supervision is kind of something similar to a transfer learning. In transfer learning, we train a model on the data from one domain. Let's say you have got the data from, let's say, Twitter. Okay, you train a classifier to label sentences there. Okay, and let's say now you got the data from, let's say, news corpus or Wikipedia or maybe Amazon data, and you want to find relations there. So the model which has been trained on Twitter data, now you want to use that model in another domain, news corpus or maybe e-market data, right? So now you are changing your domain from social media to let's say some other domain. Okay, so whenever you shift your domain and you want to make your model edit to a new domain, that's we call, you know, kind of transfer learning. The idea why transfer learning is successful is that it works under the assumption that the source domain, okay, in this case the Twitter, the target domain, which is, let's say, e-market or some other domain wherever you are working, maybe IT support ticket domain. Okay, so when you are changing the domain, the source and target domain distribution, they should not shift too much. Okay, when there is a data shift, we also call it a covariate shift in machine learning. So the target source and target data distribution should not change very much. Otherwise, transfer learning is finds hard time to adapt to new domain. Okay, so there are certain limitations of transfer learning. Distance supervision is very similar to transfer learning. So we are going to see in this coming slide, along with maybe I'll try to show the code as well. The code is in the slide itself. Okay, so that you have a better intuition. So what is a distance supervision? So here supervision term is coming. That means we will have a labeled data. Okay, we will have the labeled data because it's a supervision. We will have the two entities and the relation between them, and there is a word distance. So distance means it's a subsidiary or additional data. Okay, and the data, additional data is basically to use an existing knowledge base which has these labels, and the labels are basically relations. So somebody suppose give you this knowledge base of triples already from some domain, you have access to that. Now you have been asked to use that to build or come up with new triples, okay, from the corpus. So there are two things. One is a knowledge base. Knowledge base is basically, you can think of this where there is a subject and object and relation is there. Somebody give you this thing, okay, and somebody also give you that corpus. Corpus is your unstructured data where you want to find the triples. Okay, that's the task. Now you want to make use of this. The question is how to make use of the existing knowledge base to find new triples. Okay, so that's the idea behind this distance supervision, and let's see how it works. All right. So here we are assuming that sentences with related entities are positive examples. So yeah, and another assumption is that for negative examples, entities will not be related. Okay, so we are marking if the two entities are related, as a positive example, and for unrelated entities we are marking as negative examples. And how to do that? So let's say these are the sentences in your corpus and you want to assign whether it's a positive or negative example. So essentially we are building a binary classifier data, okay, 1 and 0s. So you read this sentence, okay, Elon Musk, co-founder of PayPal, went on to establish SpaceX, one of these, blah, 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 right? So in this sentence, what do? You check for these entities, Elon Musk and SpaceX, okay, and see in your knowledge base, what is the relation, held between these two entities. The thing is that in such kind of data, you can run your entity resolution techniques, because you need to first find the entity, right? Before you actually go and find the relation, first you need to find the entities. Yes, unless you have the entity, you cannot build the relation. So you need to find the relation, you need two entities. So let's say you have done the entity resolution thing, and you have these two entities, Elon Musk and SpaceX, and you want to find the relation. Okay, so what do? You go and check your knowledge base. Is there a relation between these two entities? And you see, okay, Elon Musk and SpaceX are there in the knowledge base, and the relation between them is founded. Then as soon as you find a relation between these entities, you make it as +1 or just 1. Okay. Similarly, you read the second sentence and see, okay, Elon Musk, SpaceX is there. You search your knowledge base. Is there any relation between these two entities? You find a founder relation. Okay, you make it as +1. Okay. And if you read the third sentence, Elon Musk dismissed concerns that Apple was poaching the company's talent. Okay, if you read the third one, you see that, okay, Elon Musk and Apple are entities. Let's check these entities are present in our knowledge base or not. And once you come up and see, you're trying to find these two entities and you see, okay, there is no relation held between Elon Musk and Apple, then you mark it, cross it. Okay, that's how you make use of an existing knowledge base to annotate your corpus in positive example or negative example. That's the idea of using a distance supervision. Okay, so is it clear how distance supervision is helping us to get more label data?
Yes, sir.
Yeah, so it's very simple. Okay, good. Yeah, so distance supervision is good. Massive quantities of training data practically free. You can, now can, label more and more data using this technique. However, there is some problem. Okay, so I invite you to find problem in this approach. Do you see, is there any issue? If we annotate our corpus in this fashion, what kind of problem you can encounter if you follow this approach? Think about. It's a simple, I guess. What can happen if you make use of knowledge base to determine the relation in the corpus? Okay, so Mamta is saying that in the already stored knowledge, if some relation is missing, yeah, good. Okay, so what happens if there is no relation? So in your corpus, maybe two entities are related, but knowledge base is not complete, because knowledge base is again coming from some domain, right? Somebody must have curated that. So what happens if knowledge base is not having that relation, which is present in the corpus but not in the knowledge base, right? That's quite a good answer. Yeah. So somebody is saying prior knowledge may not be in regard with the current knowledge. Kind of. Yeah. Okay, good. Let's see these issues. So distance supervision has certain limitations, although it's a powerful idea that you can annotate lots of data. The two limitations are that not all sentences with related entities are truly positive examples. So this is one limitation, that not all sentences with related entities are truly positive. So that means you will have sentences which are not truly positive, but they are, for example, in this case, Elon Musk and SpaceX, the two entities, okay? If you check here, you will say, okay, SpaceX and Elon Musk are there, that means there is a founder relation, okay? But do you think there is a founder relation in this sentence, right? No, yes? There is no founder relation mentioned in this one. So that's the problem, one problem. But the thing is that the benefit, now after reading this limitation, and maybe you might think, okay, it can, give false positive. So this is basically false positive, right? There is no relation, but you are saying there is a relation. The thing is that there would be some false positive, but the number of false positive would be not as much as the benefit that you are reaping through this distance supervision idea. Okay, so that's like the benefit of more data outweighs the harm of noisier data. Okay, so you can think of this is also a false positive coming because of the noise thing, right? So this is one limitation. And another limitation is that you need to have an existing KB knowledge base to start from. Okay, you cannot start from scratch. So somebody, you need to rely on someone to give you this KB knowledge base. That means you need to have an existing KB already there in your domain if you want to use distance supervision, right? So these are some issues, right? Okay, so far we looked at the task of relation extraction. Now we are jumping into, let's see if you want to, play around this task of relation extraction. How can you do that? So we are going to look at the data resources, what kind of data you can use. Then we will look at other stuff mentioned here, right? Okay, good. What are the data resources? If you want to, use distance supervisions to solve relation extraction problem, what you need is the corpus. So corpus is the data where you relation from, and the KB is the knowledge base in order to ascertain the relationship between the two entities using this KB. All right. Okay. So the corpus. We need a corpus of sentences, each containing a pair of entities. For example, you have the sentence, Elon Musk, co-founder of PayPal, went on to establish SpaceX. So what are the entities? Entities are Elon Musk, PayPal, and SpaceX, right? And these entities, how can you find? As I mentioned earlier, if you want to do relation extraction, first you need to identify the entity in your sentence. And the way you can find entity is by, what is the approach right now this question? How do we find entities in an NLP corpus? What are the entity finding techniques in NLP? Has anyone have heard of any technique? Has anyone heard of NER? NER.
NER?
Yeah. I'm not sure. Okay. So NER is basically named entity recognition. NER approach.
Named entity.
Named entity recognition. Yeah.
Okay.
Yeah,
Right.
yeah.
Yes.
So
some comments are there in chat box.
so somebody has mentioned named entity relation. Okay. Yeah. So NER stands for named entity recognition. Okay. So if you want to solve the problem of relation extraction, first you have to find the entities in your corpus, right? So I suggest, given the corpus, what you do is run the NER model. To run the NER, you can use the library Spacy is there, SPACY, or you can use the Stanford NER tool, okay, which is in Java. So you can use these libraries to annotate your data for named entities, whether a particular entity is a person, location, or a place or date and something, okay. There are many entity categories, all right. And at the same time, you have to also run entity resolution. So named entity recognition, NER, and let me also write something so that you can also take a look what I'm saying. Okay, let me open my pointer. I don't know. Okay, so okay, let me take on my page. So NER, okay, so it stands for named entity recognition, okay, recognition. So NER, if you are using NER, it can give you the named entities. So let's say the sentence is Narendra Modi is Prime Minister of India, okay. So if you run the NER, it will give you basically Narendra Modi, India, okay. So these are the named entities. So these are basically names, okay, names, countries, okay, maybe it's country and so on, okay. And you need to also use entity resolution. So NER is one technique to find out these things, entities basically. So what are these? They are entities also called entities. This is also entity. And another thing we have in NLP is called entity resolution, okay. Entity resolution. The reason is that once you find these entities, there are cases, there are sentences where it is not clear what does that entity mean. For example, in some sentences, you know, New York can mean two different things. It can be a state of New York, or it can be New York City, okay. So using entity resolution, you can find the right meaning of this particular entity, whether it is representing a state or the city, okay. So that is a problem of, let's say, polysemy and synonymy, right? So we are going to see these things in a moment. So we can, you know, using entity resolution, you can solve these issues, right? So yeah. So before you start, you know, building a relation extraction, you do this thing, run the NER model so that you can get the entities, Elon Musk, PayPal, and SpaceX, and also do the entity resolution so that you linked your entities, what do they actually mean, okay. One thing I wanted to highlight is that in order to do this one, you can use this wiki-link corpus. Here in this slide, they have used this wiki-link corpus. Wiki-link basically this, whenever you see that there's an underscore in a entity name, that means it refers to a Wikipedia page. So Elon Musk is the idea of a Wikipedia page. If you open Wikipedia page for Elon Musk, the last word in the URL would be Elon_Musk. Okay, so this is that thing. So wiki links can help you to do these things, entity resolution and so on. Okay, now we have found our entities. Now what we want to do is to find the relation. Yes, so entity we have already find. Now let's extract the relations. To do that, we'll do that in a moment. Just so Yeah, so if you want to play around this technique and want to do relation extraction on corpus, so there is data set called corpus. So they have released this library, Stanford one. So there is a corpus class, and you can use this. There is a data. Maybe I'll open once I show the notebook. There's a data also. So you can explore the data. To find or to analyze the data, what kind of relation, what kind of entities are there. So if you poke around this data using this corpus class, you can see the data which is there. Okay, it has around 300 around 300k. Okay, examples. All right, so there are total number of sentences which are there is around this much. Okay, and you open this data which is there. Let me see if I have this data. Relation extraction experiments. Maybe I'll open that one later once we have covered this thing. So yeah, so the data that we are talking about is basically of this format. So one of the examples which is stored in the data that we are going to see, it has this entity 1. If you look at one of the example, it has entity 1 as a New Mexico, entity 2 is Arizona. And what kind of relation is between them? I think relation will not be mentioned. So yeah, so left. So the way this data is stored in this data is, this corpus is basically, it has the entity mentions. That means NER has been run already. You get these identify the entities, New Mexico, Arizona. Left equal to something which is to all Spanish occupied land. It is that what is the sentence before the first entity. Okay, so left means something which is before the first entity in the sentence. And then we have this mention 1. Mention 1 is basically which entity is coming after this left. Okay, once you have this one, so mention 1 is basically your New Mexico. Okay, then the middle is basically telling how these two entities are connected. So middle would be and New Mexico and Arizona, and the right is equal to something. So right means what is the sentence coming after, the phrase coming after Arizona, entity 2. Okay, and then they have additional details, which is basically left part of speech. What is the part of speech of these words here? Okay, similarly, what is the part of speech of other things are there in this data set? So this is the data set, the corpus that we are trying to see is how this data is actually stored. Okay, so the data set mentions the entities as well as the part of speech as well as the mentions, and what is the sentence or the phrase on the left of the first entity and on the right of the second entity, and so on. So in this class, you have this well, curated data. It has been, you can say it's a pre-processed data where the entities are already mentioned. Now the task is to find the relation between these two entities, New Mexico and Arizona. Okay, so that's the task. So since relation is not present in the corpus, so we will see how can we use the KB, the knowledge base, to find the relation. Okay. So everybody following this slide, what we are doing here?
Yes, sir.
Yeah, it's a simple. You have this corpus and it has marked the entities and so on, part of his speech and etc. Okay, so there is a corpus class. So corpus class holds the examples and allows lookup by entities. Okay, so corpus. So you do this print corpus dot examples. So in the corpus there are examples. One of the examples is like this, and you can search these. So this is kind of dictionary. So you can look up dictionary lookup. If you index this corpus dot examples and then put a bracket, it will give you the entity 1 and entity 2 and so on. So it gives you easy lookup facility. And then in the corpus there is an example class. So here, basically, this data set is coming from basically the Wikipedia and so on. So if you see, they have done this, they have provided this named tuple, then entity one, entity two, what is coming on the left, what is the mention one, middle, and so on. So this is this data set, whatever we saw here. And as I mentioned, whenever there is a underscore, that means that is a identifier of that entity on the wiki page. So can you see? If you open New Mexico site or wiki page of that New Mexico, you'll see that wiki ID. Okay. So that's your entity one. Similarly, entity two is Arizona. So if you connect all these words, so here, the left part of which was here, right? Left part and so on. So here, so left, then mention one, then middle, then mention two, then right of the sentence. So if you connect all this, you will read the whole sentence, complete sentence. And after that, you have this part of speech tagging of those things. For example, New Mexico is a singular noun phrase, noun, I guess, yeah, NNP. CC coordinating conjunction denoting and. Similarly, Arizona is also NNP and so on. Okay. It's coming actually these relations. This part of speech tagging is coming from Pain Tree Bank. I'm not sure if you are aware of. Have you heard of Pain Tree Bank? Anyone mentioned in previous lecture?
Yes,
okay.
Sir. It's a latest NLP set with I think some 45 tags.
Yeah, so that these tags are coming from
Most,
their Pain Tree
most
Bank.
common NLP set, I think.
Yeah, that's correct. So these tags which are you see here, it's coming actually machine generated. It's not coming from humans. It's a machine generated tags from Pain Tree Bank. Okay. So in the corpus we have this well curated data set, right? And the idea is to find the relation between them. Okay. So if you poke around and tweak this data a little more, you will see that the corpus has, total of 95,000 entities. And the most common entities they have printed here using, by then sorting and other stuff. So this code is basically, counting how many times each entity is present in that corpus. So for example, the India comes out around this many times, England comes out this many times and so on, right? So looking at the frequency of these entities, most common entities, you will think that this corpus is about geographical entities, right? But actually it's not. There are other stuff in that, but geographical entities are most often cited entities, so that's why their frequency is very high, right, in this particular corpus. All right. So yeah, so in this corpus, if you use this class, you can actually show examples for pairs where what is the relation between the two entities, right? So if you use this corpus class and call this function, show examples for pair passing two entity names, you can easily query this corpus if there is a relation between these two entities, right? So if you do that in this particular corpus, you will see that the first 5 examples for Elon Musk and Tesla Motors are of this format. Okay. So actually there are more sentences. So they have shown only first 5, I guess. Okay. Entity 1, entity 2, and so on. And in this corpus, interestingly, there is a this is a forward kind of. First entity is Elon Musk and second entity is Tesla Motors. So it's a forward looking entity in which Elon Musk is coming, first, and then Tesla Motors is coming second, right? So Elon Musk, the relation you can guess, Elon Musk is the founder of, let's say, Tesla Motors and so on. But if you query the corpus in a reverse way, make the first entity as Tesla Motors and Elon Musk as the second entity, then you will see that, okay, there are actually sentences, okay, or examples where these entities are mentioned in the reverse order. Okay. And it can happen because the way data is present, the sentences are written, right? Because the same sentence can be written in many ways. Okay, you can write the sentence in an active voice, or you can write the same sentence in passive voice. So the entities will change. Entities will change their role, right? So for example, you can say, okay, Narendra Modi is Prime Minister of India. Okay, same entity. I can also write, okay, India has Narendra Modi as Prime Minister, right? So same entities are present in both the sentences. Okay. So if you change the first and second entity role, that's why you are getting, because of such sentences, you see that changing the entities, you are getting sentences. Yes. So that's the idea. So what is the key observation here is that the Wikilinks corpus has some flaw. There are actually some issues because the data is curated not by human, but it is coming through some machines. The reason, for example, in this particular data, it contains many near duplicates. Okay, that means the same thing is repeating. There is a near duplicate, and this is an artifact of the document sampling methodology used to reconstruct it. So the way data is sampled and the model is run, okay, on the data. So there are some issues, and we are know that when you are dealing with the real data, there are actually noise and so on, which we cannot completely get rid of, right? So in this corpus, the Wikiling corpus, another issue is that it doesn't include in any annotation about the relation, which we already saw, right? It doesn't mention is what relation is there between the two entities. So we cannot use it for fully supervised approach because we don't have the relation. Okay. So what do? If you don't have the relation, then you need to have some way, some approach to connect these two entities which are there here. For example, how these two entities are related, how to find the relation between them. So to do that, you have to use some key, some knowledge base, right? So that's how we are going to connect our corpus with the knowledge base. All right. Okay, so we are moving to now the corpus. So everybody following, not sure, people are silent now. So far, is it clear what we are doing? So somebody has mentioned POS can be optional step. Actually, that part of speech tagging is already given in the corpus, so you need not worry about that. Okay. So yeah, we don't need part of speech, but it can help you to do downstream tasks. Okay. Okay, so somebody saying corpus is an NLTK package. That's great. So somebody who is familiar with NLTK, they know what is a corpus. Good. Yeah, those who have played around with NLTK, they know if it has the corpus. Good. All right. So shall we move on, or is there any question? So the question is, how does tokenization and POS tagging differ from each other? Wow, good. All right. So tokenization is basically splitting the sentence, the paragraph into sentences. So let's say you have this sentence. Let's maybe take the same sentence which we had taken here. When you tokenize this sentence, okay, what do you get is individual words or tokens. Okay, so these are your, this is, so earlier you had a sentence. If you run the tokenization, let's say using an NTK sentence tokenizer, then you will get a list of words of this format, tokens. Okay, that's the result of tokenization. And if you do the POS tagging, part of speech tagging, then each of these words will have these tags coming from paint tree bank. It will be, let's say, NN, then this is a verb, VV, then this is another prime minister is, I guess, noun phrase. Noun, then this is your adjective, I guess, not adjective, preposition maybe, PP. Then India is another noun phrase. So if you run the POS, you will get these additional things. Okay, so that's how they are different. Any other question? Okay, let's move on. So as we saw that in the corpus, there is no relation. So that's why we are going to make use of KB to find the relation between the entities present in the corpus. So the knowledge base, so our KB in this particular case is coming from Freebase. Freebase was kind of a project by, I think, by Google or acquired by Google, and later it was shut down in 2016, sadly. So what does this Freebase contains is the triples of this format. The relation, then there is subject and there is object. So this was a kind of, I don't know, Freebase was not hand engineered, rather it was curated using some machine learning techniques from the Wikipedia page or maybe some other source, right? So they build a huge knowledge base of Freebase has less millions, maybe billions of entities and so on, and there will be millions of relation, I guess, in Freebase. If you look at the complete Freebase, and this and what is stored in this Freebase is basically these triples. For example, place of birth, Barack Obama, Honolulu. Okay, so these kind of relations are already present, and we are going to make use of these relations to extract or to mark the relations for the entities present in the corpus. So that's the idea. And here in this case, the relation is one of a handful of predefined constants. So relations are limited. Okay, they are predefined constant. For example, has a spouse is a constant, author is a constant, and so on. And subject and object are basically entities identified by their wiki IDs. So here is a Barack Obama is a wiki ID and so on. So, and this thing is present in the knowledge base. Okay, good. So if you poke around this KB class, knowledge base class, it has this KB triples, and you can again search by entity names. So now here you are, loading the KB, and you have total in this particular case 45,000 KB triples. One of the KB triples is of this format. The relation contains is hold between these two subjects and objects. Subject is Brickfields and the object is Kuala Lumpur Central Railway Station, and the relation is contains. So Brickfields contains this railway station. Okay, so such kind of things are there. You can play around this class and check whether it's true or not. And if you see the total number of relations present in this KB is actually a subset of Freebase. Freebase has a lot more relations than 16. So in this, they have used only small KB in which there are 16 relations. And if you print all the relations, I will look at 2, 4, 6, 8, 10. 12, 14, 16, yeah. So all these relations, if you poke around, and you will see that all the relations and their frequencies are mentioned here. So these are the relations present. Okay, adjoins comes around 1700 times, contains comes around 18,000 times. It's a huge, and some has very less frequency. For example, capital, because countries have the capital and there are number of countries is very less, right? So that's why you have less frequency for capital and so on. Yeah, so if you further explore your knowledge base, right, then you can print out some of these relations and the entities as well. For example, if you want to check what is the relation between France and Spain, then you see that, okay, adjoins is a relation between France and Spain. And it is also possible that the adjoins can also be, can be a symmetric relation. So if you switch the entities, maybe Spain here, first entity in France is the second entity, the same relation holds, okay? But it's not always true actually. So that's actually, you know, further noise kind of thing, or the issues with the thing. For example, here, if you consider this one, second one, right? So there is a author relation between Uncle Silas and second entity, say, D and Lee Fanu. Okay, so if you look at the relation between these two, the relation is author. What happens? Can you think of if you switch the entities, entity one and entity two, does the same relation holds between these two? What do you think? Can we switch these two entities and the relation author remains the same, or it will not be the same?
Mostly we are getting it correctly.
Yeah, but yeah, that's true. That's true in most of the cases. It will be true, but in some cases, it's not always. You know, relation is not symmetric actually. Okay. So, for example, contains. So, Brickfield can contain Kuala Lumpur Central Railway Station, or for example, New Delhi contains New Delhi Railway Station. Okay. But if you switch the other way around, if you say, okay, New Delhi railway station contains New Delhi, that's not true. Yeah. So some of these relations are symmetric and some of them are not. So that's the idea. Okay. So if you want to get retrieve the triples for entities, you can use this method or the function on this class. Okay. And if you do that, you will see that, okay, France and Germany, and the relation between them is adjoins. Now, if you switch these two entities, you will see that oh, wow, Germany and France, they are again connected by adjoint relations. Okay. So in this relation, adjoins are, you know, as we know, like if something adjoins something is, then this relation would be symmetric, right? But as I mentioned, there is no guarantee that such inverse triples actually appear in the KB. Okay, so it's not, I mean, necessary that it will happen always. Some there might be sentences in some cases, and some cases such sentences might not be present in the KB. Um, Again, if you again explore your KP, you'll see that most relations are intuitively asymmetric. What does it mean is that, for example, if you see the relation between Tesla Motor and Elon Musk, then you see that, okay, there is a founder relation. Okay. But if you switch the entities, then you see that there is a different relation now worked at. Okay. So for the same pair of entity, you see that there can be multiple relations. Yes. If you switch the entity role, you are getting a new relation between them, right? So that's also important to take care. Okay. If you are using such thing. So the order in which you are querying this KB is also important. A different relation might come up if you switch the rows of entities. Yeah. Okay, good. Again, as I said, an entity pair can belong to multiple relations. For example, in this case, get triples for entities. So here, get triples for entities, we got only one result. But if you search these two entities, Cleopatra and Ptolemy III Theophilus III, then you will see that, okay, there are two actually relations, has sibling and has spouse. Okay, so that's really strange. Such kind of triples are there where multiple relation, you know, holds between a pair of entities. So that's also possible. Yeah, so in your KB, if you count the total, so we into the KB total number of relation is 16 and the total number of entities is 40,000 approximately. And the most common entities are, for example, the country names. So it gives us some idea that looks like the KBs are about geographical names or the country things, right? But it's not, maybe because these countries names were coming very frequently, that's why they are attached to, maybe they are connected to many other entities, so that's why their frequency is very high, right? Okay, so yeah. So as I mentioned earlier, KB, this knowledge base has only 16 relations compared to millions of relations present in the free base, right? This KB is just subset of the free base, so KB is not complete. For example, such some relations might be present in some cases, but in the KB, some relations might not be present. For example, Elon Musk SpaceX, this relation is not present. Work at relation between these two entities are not present. Maybe at the time the KB was created, this Elon Musk has not founded SpaceX, right? But Elon Musk, if founded the SpaceX later, then such thing will not be there in the KB. So that's why KB is not complete. So you can take that take the KB as a grain of salt. Okay, so yeah, now we have discussed what is the task and the data resources. For example, we looked at the corpus and the KB. Now we are going to formulate the problem, how to actually find the relation between the entities present in the corpus using the knowledge base. So the idea is to connect the KB with the corpus. So we are going to formulate our problem. For example, we discuss the input and output, how to join or connect the corpus and the KB, what are the negative instance, and how we are going to formulate this problem as a multi-label classification. Okay. So what are the inputs and outputs? So what is the input to this model? Pair of entity mentions in the context of a sentence. As I mentioned, this is again distance supervision. We are going to formulate this problem as a supervised learning problem. Okay, and what we the input would be the pair of entities, entity mentions. Let's say if I give Elon Musk and SpaceX, so that's your input. And you can also talk about a pair of entities. They can be independent of any specific context also. Okay, so sometimes they have some context because they are present in the corpus. Sometimes people might query directly, okay, is there any entity between is there any relation between, let's say, Elon Musk and Apple, right, without any context. So that's the input, and the output would be the we can formulate it as single relation classification, in which we can pose this problem as a multi-class classification, or we can have it as a multi-relation classification, multiple relation classification. So just to give you some idea, so remember in our KB we have 16 relations, right? We have total 16 relations, and if I give you two entities from the corpus, so your task would be to fill this, find this relation between these two entities, to fill this blank using one of these relations, right? Out of 16 relation, one of the relation will be here. Okay, so since we are choosing one class out of these 16, that's why it becomes multi-class classification. Okay, multi-class classification. So if you want to solve a relation extraction problem, you can pose this as a relation multi-class classification, or in second case, if you see, it is also possible that we can have a multi-label classification also. The reason is that as we saw in the KB, that between two entities there can be multiple relations. X and Y can be is sibling, right, and has a spouse. I don't know what was that. So there is also possibilities, right? Or maybe to give an example, SpaceX, Elon Musk, the relation can be connected to each other using, let's say, founder relation, okay, work date relation, and so on, right? So multiple multiple relation holds between the pair of entities. So you can also formulate this problem as a multi-label classification problem. Okay, everyone with me so far? Let me check. So somebody saying not always true. I didn't get the complete context of what do you mean by not always true.
Sir, it was with reference to the triple you have shown, relation subject object.
Okay. Yeah. So that's not always true. Yeah, that's correct. Sometimes symmetric relation might be there, sometimes not. In one side relation will be there, okay, not the other way around. In KB is not complete, so some issues will definitely be there. Okay. Okay, let's move to 30 minutes, so let's cover some more stuff. So now you have seen your data. We understand the input and output. So input would be the pair of entity mentions. The output we are expecting is the relation, one relation or multiple relations. Okay. So now the task is to join the corpus with the KB. Why we want to do that? Because we want to find the relation for entities present in the corpus. For example, here you have your sentence from the corpus, and idea is to classify a pair of entity mentions in a corpus. Okay, so we want to find, when I am saying classify, that means you want to find the relation. What is the relation between the Elon Musk and SpaceX? And in order to assign or get the labels, you have to use, let's say, KB. Go ahead and use your KB. See, search for entities Elon Musk and SpaceX and see, oh, Space and Elon Musk, the relation is founder. So you get your label +1 or -1 or 1 and 0. And so that's how you get your labels. And also, so this was classifying a pair of entity mentions in the corpus. Okay. Here it is saying that classifying a pair of entities for the KB. So how would you classify a pair of entities present in the KB? What do? You get features from the corpus, because KB is not complete, right? So they, for example, Elon Musk and SpaceX, if you see, work that relation was not present. If you see here, this relation is not present, but such a sentence in the corpus might be there, where the sentence is, let's say, Elon Musk worked at SpaceX. Okay, so such sentence might be present in the corpus, but relation is not in the KB. So what to do? Okay, so what we are going to do is to extract the features from this corpus and use that. Okay, so here, let's say this is the sentence. You may also be thinking of Elon Musk, founder of SpaceX and who. So these are the sentences, and based on these sentences, you extract your feature. For example, you have this, let's say, I don't know whether these words are frequencies, I guess. So addition, I think, is coming one time, announced one time, founded one time, founder is one time. So the way you extract, maybe these are the TF, IDFs and so on. So based on your sentences, in the corpus, you extract the features. And there are many ways. You can also use word sentence vectors for these one and so on. Okay. So you are building the features from the corpus using these sentences. And what do you want to do? Once you encounter a pair of entities which are in the KB, but there is no relation, then you use these features to, train your classifier, right? So based on this data, you are getting this thing. You had this thing. For example, Elon Musk in SpaceX, right? You didn't had, remember, you didn't had the relation between these two entities, but you have the features which you can use to train your classifier to find the relation between these two, right? So that's high. That's now you see the how corpus and KB they are helping each other. So in the corpus we don't have relations, so we use KB to help find the relation, and for entities which are present in the you know uh, corpus, the entities which are present in the KB but no relation is mentioned, then you use your corpus to extract the features. So they are helping, corpus and KB, they are helping each other. Okay, so that's the idea of this slide. Okay. So joining the corpus and the KB, yeah, so if you do that, count how many examples of such kinds are there. So you see that relation, a join is coming, how many examples are there? There are lot more examples present in the corpus. So there are 58, approximately 58,000 examples in the KB, which has this relation joint. But if you see the number of triple, which is really less, right? Just 1700 triples present in the KB, right? And if you see the ratio, example by triple is huge. There's a huge gap, right? So the number of triple is very less compared to the number of example in most cases, right? So that gives some picture, right? How many times that relation appears in the corpus and in the triples and so on. So yeah, so again, to train a classifier, we also need negative instances. Remember, we want to build a binary classifier, so we need negative instances. Okay, so to find a corpus, find corpus examples containing pair of entities not related in KB. Remember, if you want to find a negative example where there is no relation, so you can go ahead and choose the pair of entities which are not related using your KB, right? So if you use this data set to find unrelated pairs, so you'll end up with around, oh my god, 200,000 unrelated pairs. So if you see in Inglorious Bastards, then Christopher's Walters, I don't know what that is, I guess the names of something. If you see, there is no relation, they are unrelated pair of entities. Okay, so using this entity pair, you can build your negative instances. All right, so positive ones are coming from here where you have the relation, and the negative are the ones where there is no relations, right? Now you have your positive labeled data and the negative labeled data, right? Okay, now we have built our data for multi-label classification. So many entity pairs belongs to more than one relation, we have already seen. For example, these are the relations which are coming together, are most common. So for example, is a and a profession in this data set is coming around 1200 times. So these are the relations which occur together. Okay, place of birth and place of death. For example, why they are connected, these two relations are coming together. For example, a person, wherever the person is born, dies the same place most of the time, right? So that's why these two relations are related, kind of thing. So that's why it's a good idea to use multi-label classification rather than multi-class classifications, right? So yeah, yeah, if you want to do binary classification, you can go ahead, and there is a approach called binary relevance. Okay, and one of the approach is binary relevance. Many possible approach to do multi-label classification. One of this method is a binary relevance. So what do we do in binary relevance is train a separate binary classifier for each label. So if Pericles and Athens entities are there, and you can train one classifier for this relation, another classifier for this one, and another classifier for this one, right? So here, if you see, for positive relation, you have more examples than the negative ones here in this particular case. So the disadvantage of this approach is that it fails to exploit correlation between the labels. So it's like in those who are familiar with multi-class classification. So using this, pair-wise, you build a classifier for each pairs, right? One of the ways to do multi-class classification is to train separate and binary classifiers to do multi-class classification, right? So similarly here, you train one classifier, you are building it's a kind of a binary classifier for each relation. Okay, so the way you go for multi-label classification is to train a binary classifier for each label. Train one classifier or train one SVM to predict whether has sibling is a relation between these or not. Train another SVM for place of birth and place of death and so on, right? The disadvantage of this approach is that it doesn't exploit the correlation between the labels, right? So the good thing is that it's a simple, you can train, a separate binary classifier for each relation. That's a good, you can go ahead and do that. Okay, so yeah, binary classifier of KB triples. So here is the problem formulation we have arrived at. So input is an entity pair and a candidate relation. The output, we are going to ask this question: does the entity pair belong to the relation or not? So now we are, formulating our problem in a different way. We are posing our problem in a different way. Now we are asking, okay, we are given the entity pair as well as the relation, a candidate relation, and we want to know, okay, does this relation holds between the entity pair or not? So it's a binary decision, yes or no. Okay. So what we are doing is a binary classification of KB triples. All right. So basically, we are given these triples and we are asking, okay, whether canvas and SpaceX are related by this relation or not. So do we predict that it is a valid yes or no or 1 and 0 kind of thing? Okay, so if you do that kind of thing, okay, and you trace the classifier, then you'll get, okay, yeah, now you need to evaluate. Remember, once you formulate your problem, you can train a classifier. Once you have trained on this data, you need to now evaluate, right? So to do that, let me check the time. We have 15 minutes, I guess. Okay, let's say we want to evaluate. So in order to evaluate, we have to split your data into training and test and development also sometimes. Those who are familiar with precision and recall and F measure. So these are the performance matrices, right? Precision, recall, and F measure, and so on. Right? So that's how we are going to follow the standard procedure in machine learning, that you split your data into train, validation, and test set, and then measure your performance on let's say precision, recall, and F1 score, or do micro averaging and so on. Right? So that's the idea. How many slides are left? Let me check. Okay, lots of slides are there. Maybe I'll show some quickly, some examples and go for questions. Okay, so yeah, so if you want to, let's say, build a multi-label classification technique based on, let's say, binary classification. So the way you can go ahead and do something via this approach, test-driven development. So in software engineering, we are known that, okay, there's the agile software technique and development technique, and there are many other ways to do that, right? So in machine learning, one of the mostly used technique is the test-driven development. First, you write unit test and check whether the code works, and then start writing the code and iterate the process. And there is another paradigm of good model engineering approach, in which you first build a test harness that performs a quantitative evaluation, and then start building the model, hill climbing on your evaluation, and so on. So yeah, so as I mentioned, once you have your data set and choose the classifier and so on. So now next task would be to split your data into multiple subsets, right? So here we have tiny, train, dev, and test split. Tiny is just 1% to write bug-free code. So you use 1% of the data to, that's how I actually follow. I first write some code to, maybe to, let's say I want to do linear regression on a small on big metrics. So instead of loading all the big metrics, I'll cook up a toy data set of let's say 1%. In this case, you write a good code which is bug free. Once you are sure, then you go ahead and train it. Okay. So that's a usual approach of splitting. Then you tune your hyperparameters on the development set, check the generalization performance, and then after that you can go and deploy and test it. Right. So that's the usual approach. I think all of us are familiar with this one. Okay. Okay, so splitting the data, the ideal way. So how to train and test or how to split. Okay. So yeah, I don't know if this slide tells you something. Let's directly go. Actually, we have more slides to cover. So here actually on these slides they have mentioned how to actually split the data. Okay, it's not so simple. If you talk about this splitting the corpus and the KB, it's not that simple. Okay, so the way it is suggested is to first split the KB triples by subject entity. Okay, for example, we have the subject and then object and the relation, right? So the idea is to first split the KB triples by subject. Okay, then split the corpus examples. If entity 1 is in a split, assign example to that split, or if entity 2 is in a split, assign example to that split, otherwise assign example to a split randomly. Okay, so basically here our idea is to choose entities which are present in the corpus according to the subject entity. You check whether this subject entity is there in this corpus example that you are checking, whether it's the first entity or the second entity and so on. Right, so here you can use this code to split your data set into these tiny driven, and I mean the same way the way scikit-learn provides, right? So that function you can use to directly split into these three fraction. What fraction should be used to split that one? So I mean it's really handy to use this feature directly, and you can see how many examples are there in each split, right? So you can use this function directly without worrying too much. So yeah, I hope people are familiar with precision and recall. Tell me if anybody is not familiar with precision and recall so that I can iterate. Okay, so I hope people are familiar with precision and recall. So yeah, so precision basically tells you what is the fraction of correct prediction in the total predictions, right? And recall tells you that out of total truth, ground truth, how many are actually returned by the model. Okay, so that's your recall. And accuracy, I think everybody is familiar with. You sum the diagonals and divide by total, so that's your accuracy. So we are going to use this precision and recall. So, and there is F1, where F1 is again harmonic mean of precision and recall that we can use to assess how good our classifier is doing. So yeah, so this is another way to express your F1 score using F beta. So in this case, in this particular problem of relation extraction, actually we use, instead of F1 giving equal weight to precision and recall, the preferred approach is to give more weight to precision. So that's why you put this 0.5. So it gives the weightage, how much weight you want to give to precision and recall. So the preferred metric to use in this relation extraction is to use this one, which because we are more interested in precision. We want to retrieve as good as correct precision as good ground truth, correct ground truth as possible. Okay, so we want to increase basically this value. This value. Okay, in this ratio 3/5, we want to increase this one. Okay, so that's why you can weight your precision and recall using this formula. Yeah, so and then finally there is another metric over this one called micro averaging and macro averaging. So I suggest you go and check, you can read about this one, so how to take the micro average. So micro averaging gives equal weight to each problem instance. On the other hand, macro averaging gives equal weight to each relation. Okay, so that's the difference in this case. And yeah, if you run this thing in this particular case, so the performance is around for classifying the adjoint relation. Remember, we are training classifier to predict the whether the relation holds or not. Okay, so if you do that, you will get for 100 instances, the F1 score is 0.7. For author, the F score is 0.8, which is really good, I guess. And if you increase the number of instances to 1000 for, let's say, content relation, the F1 score goes to 90%. That's really good. And here, you can see the how micro average and macro average has been used. So in micro average, you are giving equal weight to each problem instance. So here problem instances are different, but in micro averaging you will give equal weightage, and when you go for micro average you give equal weight to each relations and so on. So that's the idea. Let's not go into, let's look at simple baselines so that we can compare. Simple baselines are random guessing and common fixed phrases and simple classifiers. So I'll suggest that you take a look at this picture. So if you want to build a simple baseline using random guessing, so randomly I will predict the relation between two entities, right? If you go and use this approach, just a simple random classifier, you will see that recall is generally 50%, right? If you see the recall column, micro average is around 50%, but precision is really poor. It's just 8.4%, right? So if you're using this random classifier, then we are not getting good F1 score. It's just 9%, right? So because random classifier can randomly say, okay, this relation for this entity pair is there and this relation is not there and so on. So that's why using random classifiers like coin flip. So if you are randomly predicting whether there is head or tail in, let's say, 100 tosses, you will end up using because of law of large numbers, who are familiar with, I guess, right? You will get, let's say, 50% of the time head and 50% of the time tail. So if you are using random classifier to do this kind of classification, your recall would be 50%. The precision is not good. The reason is that you're out of total predictions, the correct predictions, out of total positive predictions, the correct prediction will not be very much. So that's why you're getting low precision. Okay, so there are a lot of other code. I'll show another one if they. Yeah, so if you use this common simple baseline common fixed phrase where they change something, some phrases, then they see that, okay, the F1 score goes to around 11%, right? So this, earlier you had this one 9%, now it goes to 11% using this technique, common fixed phrases, right? And finally, if you use this simple classifier bag of word feature, those who are familiar with bag of word feature, okay, if you use such features to train your classifier, then let's see here, they have trained a logistic regression on bag of word features. I think using which is built there. So let's see the performance of this logistic regression using bag of word features, right? So it gives you around 56%. That's really great boost to F1 score, right? Simple bag of word features and logistic regression, you get really awesome performance, right? Okay, so I think this is the same result. So further directions to explore would be you can examine the trained models, and you can discover new relations which are not present in the KB. Okay, as we saw that KB is not complete, so you can use the features present in the corpus to find new relations, right? And then thing would be to enhance the model and so on, right? So I think I'll stop here and let me know if you have any questions, okay? So that we can clear some doubt if people have.